Okay, so we've seen that we can use this this method of the integrating factor to solve a first order linear differential equation of this form. The form is y prime plus p of xy is equal to q of x. We've also seen that the integrating factor is defined like this. Mu of x is equal to e to the integral of p of x dx. It seems kind of arbitrary. How did we get that? Why does that work? Well, let's find out why. Remember, the method involves multiplying this whole first order differential equation by mu of x. So mu of x times y prime plus mu of x p of x y is equal to mu of x q of x. But why do we do this? Well, remember our goal is to actually solve for y. We want a function y in terms of x. We don't really want y prime, we want y itself. So what we kind of try to do here is we get this left side into this form we want. We want it in the form mu of x y prime is equal to mu of x q of x. So now we see we don't have y prime anymore. We just have y inside this hole, inside the parentheses, which is differentiated, which has itself a prime. From here, we can actually take the integral of both sides. Then we get mu of x y is equal to the integral of mu of x q of x. And from here, it's pretty simple. We just divide by mu of x. So we're going to get y of x equal to 1 over mu of x integral mu of x q of x. So really, you can always solve a first order linear differential equation just by using this formula. You can really just solve it by plugging in this formula. It works every time because this is the standard form. But why does this work? Why does this mu of x that we mentioned over here actually work? So it only works if it's true that this is equal to this. So how do we determine that? Well, we can actually just take the product. We can actually use the product rule to find mu of x, y, all differentiated. So if we use the product rule, this is just going to be, well, remember the product rule is just f g prime is equal to f g prime plus f prime g. So if we use that simple product rule from Calc 1, we can get mu of x is equal to mu of x times y prime plus mu prime of x times y. And so what we're going to get is that mu of x, y prime, is equal to, mu of x, y prime, plus mu prime of x, y, is equal to mu of x, y prime, plus mu of x, p of x, y. So we can notice that the mu of x, y prime terms cancel. So really all we have left is mu prime of x, y, is equal to mu of x, p of x, y. And then the y's cancel here, so we're really just left with mu prime of x is equal to mu of x, p of x. So we're almost done. Now we can really just recognize this as a separable differential equation. And we can pretty easily solve for the integrating factor here. So we can rewrite this integrating factor of the prime here in Leibniz notation and just do d mu dx is equal to mu p of x. So if we kind of multiply each side by dx and we divide by mu, we're going to get d mu over mu is equal to p of x dx. Now if we integrate both sides, we're going to be left with ln of mu of x, let's write mu of x now, is equal to the integral of p of x. In order to get rid of this ln on this left side, so we're just left with mu of x, we're going to raise both sides to, we're going to exponentiate both sides. We're going to take e and raise it to each side. So we're going to get mu of x is equal to e to the integral of px dx. So that's exactly what we wanted. That's how we solve for the integrating factor. And remember, that comes from needing this left-hand side here, this mu of x y prime plus mu of x p of x y has to be equal to this mu of x y all primed. That's how we determine the formula for the integrating factor, and that's why it works.